Okay, yeah, I think we are good. So Sunil, if you can take over.
Yeah, sure. Thank you. Good morning, everyone. So this is our third session on Hadoop, and I'll just give you a small brief introduction about myself. As Debashan has already told you, we work together on the same team. So I'm part of HD Insight team. And today in this session, I'm going to introduce you to MapReduce. In fact, I don't even have a single line of code or any Java code or C# code here. All I will be explaining you here is what is MapReduce and what is shuffle phase, and how the job tracker and task tracker come into picture, and how whatever we covered last week, like the node name nodes, data nodes, job tracker, task tracker. If we are able to get to know how all these works or hand to hand or go together, that my objective for the day will be accomplished. Okay, so it's all about basic understanding of MapReduce. That is what we are going to cover in here in this session. So in this, in fact, let me go ahead. Okay. So this is our agenda. So we will recap whatever we covered last week. I will try to define MapReduce. I have a small analogy which I keep explaining everyone whomever meet whenever they ask me about MapReduce. I hope the same analogy is successful in clearing your or clarifying your doubt about MapReduce as well, and then different phases in MapReduce. The session for today is very light. I just want you to have a very good understanding of MapReduce as such pertaining to Hadoop. That will be my objective for the day. Now, here is a quick recap. In the first session, we discussed the motivation for building a massive parallel processing environment. Debashan had already covered what is big data and why do we need Hadoop and things like that. So, and we all know the motivation is to effectively, first thing, manage the data, enrich them, and gain insight from the data that is already residing. So we know that big data. When we talk about big data, it's a massive data is a massive scale. So we should be able to easily manage this and also make sure that we draw insight from this data. That is our objective. So this is our motivation which led to Hadoop. So this we covered big data in the first session. In last week, we discussed some challenges that exist while we manage big data, be it storage. How whenever we store a big data on a large, very big size hard disk, how the access speed gets delayed or the hardware failure. So quickly, today I will start the session with this quick recap of what we discussed last week, which was about HDFS, and then proceed further, and I will introduce you to MapReduce. So with this recap here, initially we started access speed. We compared how within 10 years from 1980 to 1980, how the hard disk size or the capacity in which you can store the data on a hard disk increased, whereas the access speed did not keep up with the storage size. Okay, so that is what we discussed first thing, and then parallel processing data in parallel, which is better. I told you how. Instead of having a one big CPU and having a hard disk, rather than having a massive cluster, a massive machine with one big hard disk, it is better to process the data in parallel. And we also discussed clustering, how the traditional architecture works and how the cluster architecture works. Okay, why cluster architecture is the way to go. Okay. And we also discussed why it is effective to store data on multiple machines and access them in parallel. Okay, and that is how we discussed and how Hadoop got started. We discussed how the Google pages, Google released few white papers, which Yahoo and some team from Yahoo picked up, and it started with Nudge. And also we discussed about HDFS architecture, block size, what is name node, what is secondary name node, and how whenever of the image files, we discussed how the metadata gets stored in the name node, and how secondary name node keeps a backup of the name node. Okay, and every now and then how the read and write works, and all of those we discussed in our previous slide, and as well as how the write happens. Okay, this was a very brief introduction that I gave you how the HDFS write actually happens. These are some of the things or some of the points that we discussed last week. Okay, and the primary focus was why HDFS and why they came up with cluster architecture for Hadoop as such. Okay.
Yeah, so for guys who missed it, you can again go back to the YouTube channel and see the recording, just for your information. Okay.
Yes, absolutely. So today, let us start by defining MapReduce as such. Okay. Now, MapReduce is I've just picked up this from Hortonworks data platform. Okay, I should have given a link for that, but anyway, so this definition is from Hortonworks. So what it says is MapReduce is a framework for writing applications that process large amount of structured and unstructured data in parallel across a cluster of thousands of machines in a reliable and fault tolerance manner. Now, there are so many things here. All I have highlighted is few keywords here. First thing, MapReduce is a framework. When we talk about a framework, it provides you tools with which you can build a MapReduce program. Apart from writing, it also assists you in compiling the code, executing the code, and all of those. Okay, so it is a whole lot of framework. MapReduce is just not functional programming as such. It is just not a sort of compiler. Rather, it gives you starting from writing a code, executing your code, all of those. The entire it's a whole lot of framework that is shipped with your Hadoop. Okay. Now, why do we need this MapReduce, or why do we write this? So, our primary concern is you have already stored your data in HDFS. Now, how do we process this? Because HDFS stores the data on multiple machines, and the data is scattered all across the cluster. So, the data in that case, your programming framework should understand how the data is already stored on HDFS. So in fact, when MapReduce was built, it's not that MapReduce and HDFS was built one after the other, but they go hand in hand and they were sort of planned in parallel, okay? So it was planned such that, okay, we are going to scatter the data all across the nodes, and then we should also have a programming framework which can go ahead and pick up this data and process against it. So MapReduce can process large data specifically, and I want to highlight, this is a parallel. It processes the data in parallel. Okay, and it could be structured or unstructured data. When we talk about reliable and fault tolerance, it is built within the MapReduce such that if it is unable to, in between while it's processing the data, and if it is unable to complete the processing of that specific data, goes back to the master node, says that I was unable to complete, and it can pick up. It is reliable and it can go accomplish the job or complete this job from a different node altogether. So all these are built within this MapReduce. Okay. So these are the highlights. Like, it is a framework. You can write applications to process large data. It could be unstructured or structured, and the processing of the data happens in parallel. And the fault tolerance and reliable is all built in within this framework. That is how it. So, if you can see, this absolutely complements the idea of storing the data distributedly, which is accomplished by HDFS. Now, I'll just start with this analogy as I mentioned earlier. Okay. I have taken an example of India. Okay. So, what we have here is, you have some 6 blocks of before I start explaining what these blocks are, I have taken an analogy of census. How a census happens within India as such. Okay. Now,
should say Bangalore, Sunil.
yeah, this is primarily within Bangalore. You're right. So these are few locations. I have picked up 6 locations within Bangalore, and east, north, south, west. I picked up few locations within Bangalore, and I prefixed with where it is situated as such. But that is not very important at this point of time. All I want you to get to know is, if you see the usual census that happens, there is a teacher who comes to your door once in 2 years or 3 years. She captures the data, and then what happens is they collate the data, or they collect all this data from one area, and again there could be a central location. Okay, let us say for Marthali, there could be a central location in Domblur. Everybody from Marthali, Whitefield, Kerpuram, these are locations within one location, like a part of Bangalore. From east part of Bangalore, there are 4 or 5 locations. So there could be a central body or a central organization which picks up all this census data. They shuffle or they go through this, and they might combine this together. And again, this similar to east, west, and east, west, north, south. There could be a centralized location which picks up all this data from all these 4 areas, which collates this, aggregates this data, and you will get to know, okay, Bangalore has got this much population. Similarly, it could happen with Mysore, Bangalore, or again, the data is collected at the district level and the state level and the country level. Okay, so I have taken the same analogy here, but I have taken down a very small piece. Within Bangalore, I have picked up 6 locations. So now, these individual files that are, let me check out if I get a pointer. Okay, yeah, these individual pieces are some like houses as such. Okay, now the first piece I want to highlight here is there are some school teachers or some people who go to individual houses. They pick up the data. Okay, what data? What is your name? How many people reside in your home, and your caste, religion? I think all those were included in latest census. So they pick up all this information. Okay, there are individual teachers. They go to houses. They pick up the data. Now, what happens here is I have just slightly tweaked. Okay, now for location. Okay, what I have done is they segregate the data depending on the location. So there could be 2 central locations. Okay, 2 central bodies or block within Bangalore, and these 2 guys, what they do is they capture the data, everything from A to M. It means every location which starts from A to M, all these goes to one body, and everything which starts from N to Z goes to another body. So in that case, the first thing, the Kerpuram falls between the first location. So all the data from that will go to that specific municipal body or anything. Okay, this S starts from, and then this goes to the Sarjapur area, goes to a different location. The Elanka goes to one specific location. Hebbal again falls between A and M. JP Nagar falls between A and M, and Rajanagar falls between A and M. So what we are doing here is we are segregating the data, okay, based on the location. So everything pertaining to the locations are segregated between these 2 blocks as such. It could be 2 locations within Bangalore, okay, yeah, as simple as that. Now next, what happens is this entire data that we have captured is merged together, which gives a whole data for Bangalore as such. So what are we doing here is we are picking up the data, splitting up into 2 different bodies, and those guys, it's easier for them again to collate or aggregate the data. And another thing that they are doing is it is easy to sort. Sorting is a very important piece. You have to keep this in mind whenever we are running, whenever we are manipulating with data. Sorting is the most time consuming and the core concept or a core piece that we need to keep in mind. Okay, so here what we are doing is we have sorted the data at the very first location, and again it makes easier for us to aggregate and then display the data. So this is how our census could work. Okay, this is how I assume to be working. Now 2 pieces I want to highlight here is, first thing is we sorted the data between A and M, N and Z, and then we merged the data. Okay, now after merging, we will get to know from within Hebbal there are these many people, within JP Nagar there are these many people, Kerpuram, Rajesh Nagar. So we have merged this, and if you can see the merged data, even that is in sorted order. Okay, even that is in sorted order. I haven't picked up the numbers because that is not my highlight. All I wanted to explain here is First thing, you have teachers going to individual houses, capturing the data, sorting this data, and then merging this data. This is all I wanted you to explain. Your MapReduce jobs almost works similar to what I have explained here. So I will explain you what is compute node and compute node and data node and all of those earlier. But keep this in mind. Teacher goes to the house, captures the data, and they sort it out on the first stage and then merge this. Okay. So if you understand this analogy, the next piece will be very simple. So let us get into map and reduce phase here. Okay, what do we have under map and reduce phase? First thing is, this is like a book. I've split the book. If you can see, this is to be a side of the book, as simple as that. But yeah, so you have a huge book, okay, which have our end goal. Our end goal is to count the words within this book. Okay, if one guy has to read that entire book and count the book, he will take maybe a month or so. Okay, instead of that, like it depends on the pages and how the reader reads the book, how efficiently he can read the book. Okay, these are two things that we need to highlight here. So let us say you have some 1,000 pages in this book. If one person reads this 1,000 pages, he might take 100 days in such that he reads 10 pages every day. Okay, if he reads 10 pages every day, he might take 100 days to read this 1,000-page book. Now, if there are 10 people reading this book, it would take just 10 days, okay, just to read this entire book. Or you are splitting that entire workload across 10 people, which makes the job easier as such. So the same thing that we do within your map and reduce phase here. So if you remember the way in which we had spread across the data, we have split our huge file, one big file, across 9 number of data nodes here. Okay, so this is we have entire book, we have loaded into almost 5 data nodes here. All these data nodes or all this data is fed into a mappers. Okay, so instead of one machine reading this entire book and calculating and aggregating the words, rather what we do is we split these books. We split this book into 5 different blocks, and then we feed individual blocks to specific computer, okay, or the specific node. So individual node, which is parsing these lines of individual lines, okay, and it is doing some computation against the line. So individual nodes is called a compute node because it parses individual lines from the book and it starts calculating the words. I will further explain this, but all I wanted to highlight was what is a compute node. A compute node is a node which picks up the data and it is acting or it is doing some action against this particular data that we have fed in. But the next thing that happens is whatever data that we have done, it reads that individual lines, it sorts, shuffles, and it forwards it to the reducers. What this reducer job does is, all it does is, it does aggregation. It aggregates the data and it stores into HDFS. Now, if you compare with the previous slide that I mentioned, that individual compute nodes are the teachers or the person who is capturing the data. Okay, he goes and picks up the data, and the reducers are nothing but the intermediate organization or the body which picks up this data, sorts, shuffles, and finally they aggregate and store this. So I would certainly ask you to go back and compare with the analogy that I have given you, so that it's easier for you to understand. Okay. Now, 2 things I want to highlight. The data that we have feeding into the mappers should exist on HDFS. The sorting and shuffling, the intermediate data that is created by these mappers are not stored on HDFS. Rather, it is stored on the local disk on the data node itself. Okay. First thing, the data which is fed into mappers are on HDFS. Second piece, the intermediate data that is spit out of the mappers are not stored on HDFS. Rather, it is stored locally on the machine itself. Why doesn't it store on the HDFS? Because many a times this whatever data that has been spit out of these mappers or not fully done. Maybe in between, it starts flushing out, it starts buffering to the file, and it could be possible that in between, while it is computing the data, one of the nodes can go down. So in that case, again, it has to go back and redo the job. So whatever data that it has buffered, if you start storing it into HDFS, you might have to clear and all of those. You might have to rework the data. So that is the reason the shuffle and the sort and the shuffle data or the intermediate data that is spit out of the mappers are not stored on HDFS. Rather, that those data is directly stored on the local hard disk, which is fed into our reducers. The reducers are again a compute node which does aggregation on this input and then stores this on the local hard disk, which is on HDFS. Okay, the first and the last, the input and the output should always be on HDFS. The intermediate data doesn't get stored on your HDFS. That's a highlight. Another thing is you can draw an analogy from this slide with the previous slide, okay, where you go to the data and read the data. So you go to the data and read the data. I just wanted to highlight because that is again a very highlight of MapReduce and things like that. Okay, now let us try to understand. We are trying to build. Okay, every slide tries to build upon the data or the information that we captured from the previous slide here. Now what we are going to do is we have an input file. This is a word count example. Okay, we have an input file, a text file which has got some words into it. It could be a poem or it could be any data. Okay, and I have tried to split out this individual file into various stages that it has passed through, and also what is the input and what is the output that each phases has. Okay. Now our input is 3 lines that we have here. This is input, and I just want to count how many times individual words appear. Now the first thing that happens is splitting. Each and every data is split. The data that we input is split into. It's not that every whenever we feed the data that it's split into individual lines. It depends on the input formatter, okay, which I will be discussing in the next slide. But in here, we first split the data. Now, this whatever data that is split is an input to the map phase. Okay, near here is an input to the map phase. So whatever data that we are feeding into the map phase should also be in key value format. But all you see here is just some values. What happened to the key? I'll explain further how the keys also come into picture. But just for easier understanding, I have skipped that from the splitting phase. So first thing, if you can see the bottom here, I have told the input to the mapper should be in key as well as key and value pair. But all we have is some values here, but the keys are missing. That is fine, absolutely fine. Okay, this is just for understanding here. Now, within the mapping phase, what we do is each and every word, it parses or it reads through the individual records, and it says, okay, it adds the value to it. Okay, near appears 1, here 1, here 1. So as you can see, within the mapping phase, you are mapping some, for the key, you are just mapping some value here. And next, within the shuffling phase, okay, within the shuffling phase, primarily it so happens during the shuffling, it does a lot of sorting as well. Okay, it does a lot of sorting and shuffling both. Now, the phase is called shuffling, but in fact, it does a sorting here. So if you can see, if you can see the 3 blocks, it has already been sorted. Okay, and then within this, whatever is in the shuffling phase becomes an input to the reducer phase. Now, what is the input to the reducer phase? If you can see, the output from the mapper phase is just a key and a value, but the input to the reducer is a key and a list of values which you can iterate. 2 things. The input to the reducer is a key and then a list of values which you can iterate through. Okay, so if you can see the shuffling phase, you have a key, okay, and you have multiple values which you can iterate and add and say here is true. So what this reducer does is, as I mentioned, reducer, all it does is aggregation. So he has added up here with, if you can see this, he has added up 1 plus 1, and he has this phase has said 2. So dear one, the same thing happens with here. Okay, now I think I have removed this here. Anyway, so if you can see the shuffling phase, again, within this map and reduce, they all point, they narrow down to, within the reducing phase, there could be, in mapping phase, you can have multiple compute nodes, but in reducing phase, the compute nodes will get decreased. Okay, will get decreased, and they get mapped to it, the individual reducers. It is not that part of the year will go to the second reducer and part of the there will come to the first reducer. No, that doesn't happen. They here marked, and they are specifically, once it is sorted, the key, based on the key, it goes to the same reducer as such. Okay, so few highlights here. The input to the reducer is a key and a list of values, and the values should be iteratable. And another piece is whatever is getting into reducer is already been sorted and specific, and the keys doesn't get distributed. Like if you see here, if there are 3, 1 doesn't go to the first reducer and 2 will not go to the second reducer. That doesn't happen. Based on the key, it goes to the same reducers. And finally, the output of the reducer is just an aggregation. Okay, this is the final result that we have. It is nothing but a key and the sum of or aggregation of the values that was included. Okay, so very quick recap. The inputter to the mapper is a key and a value, and the inputter to the reducer is a key and a list of values. And what does this reducer does? The reducer aggregates the whatever input that has been fed into it, and apart from this, whatever input that goes to the reducer is already sorted. Okay, and if you see the sorting or the shuffling phase, you don't have to do any extra work for it. Whenever you're writing a code, or whenever you're writing a Java MapReduce or a C# MapReduce code, you will have a map and a reduce method, but you will not have a shuffling method. It is done internally for you. There are other phases as well, as like combiners and partitioners and things like that. I will cover partitioners, but yeah, these are all done internally. But at the very high level, you should absolutely know what is map and what is a reduce phase. I hope I was able to explain that in detail with this slide. Okay. Now I have a quick I have another example here. Okay. So let us remove this. Now let us take this simple rhyme here. Twinkle, twinkle, little star. So how does a mapper, or how it exactly works? So it depends on the input formatter. There are quite many input formatters. There are database formatters and record formatters and quite many. But the default input formatter is a text formatter. So how does it happen? What exactly happens is the individual lines are split and they are fed to mappers. What is the number here? Okay, key. What is the number here? This is just an offset. Usually it starts with 0. Okay, it starts with 0, and this will be 30 and 27. So if there was some other line here, let us say so. This is how it starts. So you have an offset of how many words are there in this split. Okay, and then this individual split are fed to the mappers. Now, so what happens with the mappers is this is the output from the mappers. This is the input to the mappers, and this is the output that each and every word appeared how many times. Okay, and if you can see, so this all it does is it just adds a value to it. Now, the above output from the map function is processed by map. Now, what happens here is the entire data is sorted. Okay, the entire data is sorted, and then if you can see twinkle appears 3 times, so it just adds up 1, 1, 1. So now this data is again fed into your reducer, which aggregates this data. So all of the above will have 1, only the twinkle will have 3, because that is, I guess, it appears twice. Okay, so this is how it happens. There is additional offset which also gets keyed in, or which also gets added up, which is fed into the mappers. Now, so here, what I would like to highlight here is this is the same slide which I picked up from which I had already shown in my previous session here. Okay, all I wanted to highlight is you have a server, you have files which are block sizes, which are blocks of, by default it is 64 MB. Okay, now what exactly happens is you have all these data that is stored on these individual files are stored on your name node. Okay, the block size or the blocks where the blocks are stored are already, all this metadata information is stored in your name node. Now, all we have to do is we have to send this code that we have to individual servers. Wherever the data is residing, we need to send the mappers to those specific servers to get executed. Okay, that is our objective now. All this time, all we were trying to understand is what is map and what is reduce phase. Now, the next piece that we are trying to understand is how the code is sent to the individual servers.
So, Sunil,
wherever the data is residing.
So, yes. When you say individual servers, do you mean individual data nodes, right?
Individual compute nodes, yes, you are right. Individual data nodes. Okay.
Yeah.
Okay. So, yeah, we also need to understand that this entire 4 machine could be a part of a cluster, and this cluster contains 4 servers, and all the data that we have, all the data that are already stored on these 4 clusters, it also takes care of the replication, and all of those are already, all the HDFS piece is already been accomplished on these servers. Okay. Now the next piece is how we are going to send the code onto the compute nodes. That is all, what is the highlight of this next piece. Okay. Now, we will try to understand the roles and responsibilities. We know our data is already residing on a number of machines. So we have to send whatever word count that we want to accomplish on the data or on the book that we have, which is stored on multiple nodes. We need to count the words. So the first thing that happens is there will be an entity which is submitting, which submits the job. Okay. Or there is a client which submits the job. The job in here, let us consider, is a word count job. Okay, the word count job is submitted by a client, and to whom will it submit? The word count job is submitted to a job tracker here. Okay, now, first thing is, the word count job that we have is a MapReduce job, and this is the unit of work the client wants to perform. Okay, the job client that I have mentioned, he wants to perform a word count on all the data that we have stored on our HDFS. So what are things that this guy needs? First thing is the input data, the actual MapReduce job, and the configuration. The configuration could be how many reducers should I use, or it could be where or how the block size are, anything. Okay. First thing, the input data. Second piece is when I talk about input data, where the data is located on HDFS. The second piece is MapReduce program. In this case, the MapReduce program is nothing but a word count. And third piece is configuration. These are the 3 things that this job client requires. Okay. So This MapReduce job is actually divided into tasks by Hadoop. Okay, and by Hadoop. And this Hadoop runs this job by dividing this task into two other tasks, that is map task and job reduce task, which I have already explained how those two works. Okay, and a job tracker. A job tracker and a bunch of task tracker controls the entire execution. Okay, I will explain you what is job tracker and task tracker. But all I'm trying to do is introduce what all things are, what we already know, and what things we are going to explore. So the MapReduce job is first divided into map task and job task by map Hadoop, and then this map task and job task is taken care by job tracker and task tracker. Okay, now the client submits the job to the job tracker. Apart from submitting the job, it copies the binary. Okay, it copies the mappers and the reducer implementation, whatever code, to make it simple, whatever code that we need to run against this book that we have to run a word count, right? Whatever mappers and reducer implementation that we have, along with the configuration information, okay, and the input and output paths, all these are copied. And first thing is the map and reduce job, and that is copied onto the HDFS. Okay. Now, when we talk about in the previous slide, I mentioned that the code is brought to the actual word count code is sent to the data nodes. Okay, that is how it happens on the very first stage. When you submit a job to when the job client submits a job to the job tracker, it also picks up the code that needs to be run on the data nodes and copies them to the HDFS. That way, the code that needs to be run on the data nodes are already available on HDFS, which the task trackers can pick it up. Now, what is a job tracker? This guy takes care of the entire execution. Okay, the entire job, whatever job that needs to be, it orchestrates the entire job as such. Few things. First thing is, we have in our job client, we have mentioned our data is located on specific HDFS location. Now, what this job tracker does is it picks up that input whatever input value that has been submitted by the client. It picks up that location, goes to the name node, queries the name node. It asks where all this data is located. Can you give me? This is a huge file, and this data is spread across n number of nodes, data nodes. Give me what all nodes the data is located. It goes to the name node, picks up the data location. That is how the job tracker gets to know, okay, I need to trigger the task trackers running on the data nodes which the name node gave me. So first thing is, the job tracker picks up the input location that was submitted by the client. It goes to the name node, queries, asks the name node, please give me the data node where the data is located. The name node gives a list of data nodes where the data is located. Now the job tracker picks up this, and he is aware, okay, the data is located on n number of data nodes, and he is aware where all the job needs to be submitted and what all nodes the task tracker has to be triggered. So the job tracker creates an execution plan. It says, okay, I need to trigger the task trackers residing on these number data nodes. Now, how does this happen? It is not that it happens randomly. Rather, it looks for a data localization. What happens is, if there is a racks, if there are racks, if there are 3 racks, and if the data, it looks for the data which is residing on one single rack. Okay, so if the data is available within the single rack, it goes to those racks and runs the task tracker. Or else, if some data is available on rack 1, rack 2, and rack 3, it goes to all the 3 racks and executes the job. But it also looks for data localization. That is additional piece. Even if you don't understand, you can just skip that part for now. Okay. So all we have to understand here is job tracker has got an idea where the data is located, and it goes to the task tracker. It triggers your task tracker and says, go ahead and do your job, and what job that it has to do. Okay. Now, before even submitting the jobs to the job tracker, it also checks out if the slots are available on those specific job trackers. Okay, and those specific task trackers as such. Okay, now now the task trackers are triggered by the master job tracker. Now the task tracker starts working. What does it do? You already have the code or the binaries that it has to execute, okay, against the data. It starts doing this job, and it keeps pinging, or it sends a heartbeat back to the job tracker stating that I'm working on the data. It keeps pulling back to the job tracker. This is how the fault tolerance works. The task tracker keeps pinging the job tracker stating that I am doing the job every now and then. If it doesn't get a heartbeat for some time, the job tracker will consider, okay, there is something wrong with the data or the computation that was happening against on this task tracker, on this data node. Let us leave that aside and let us check out what is the block, if the same block is available on any other machine, and let us trigger the task tracker on that other machine. If the slots are available on another task tracker, it will go and start executing the job on the other one. So this is how that fault tolerance works. So the task tracker keeps sending messages to the job tracker stating that I'm doing the job. In case if the job tracker doesn't get the message for a long time from the task tracker, it will consider, okay, the job is not happening, or something is wrong with this compute node on the data node. Let us move on, and then it will trigger. It will pick up the same information which is already got. It knows what data node has failed. It will try to look for the same similar data node on a different compute node. Now, if you understand HDFS, you have replicated the data. By default, you can replicate the data 3 times. Okay. So if one of the data node fails, it will pick up the second data node where the same data is available, triggers the task tracker, and start executing the job there. So this way, the job tracker manages the phases and then finally updates the success as well. Now, the phases, when you talk about managing the phases, all we have discussed about is map job. The task tracker keeps executing the map job. Once the map job is done, it goes back to the task job tracker, and that guy shuffles the mappers again, shuffle the data as well, and then it is a job tracker's job again to introduce the reducer. It is not as, if you look into the slide that I had explained here, it is not that every time if you have a number of mappers, it's not that you will have the same number of reducers as well. No. Okay, the job tracker it will check out how many job trackers or how many reducers that I need to accomplish the job here or to do the aggregation. This is configurable. You can, whenever you're submitting a job, you can configure stating that I need these many number of reducers. So the job tracker will introduce that many reducers for you. Okay. So you have map phase which happens on the task tracker, which sends back the information to the job tracker. The job tracker again picks up few task tracker to get your reduce job done. Finally, when the entire map and the reduce phase is accomplished, it updates the status. Now, what is the job of your task tracker? All your task tracker just does is it executes the tasks. Now, what are the tasks? There are 2 tasks which I mentioned, map task and reduce tasks. So both these tasks are executed by your task tracker. Your job tracker, all it does is he orchestrates the entire job, makes sure who is going to execute and whether he is executing it or not. If he is not executing, let us move on and let us get another task tracker in place. So your job tracker, all it does is it keeps a track of how the entire execution is working, how the entire execution is happening. Okay. Now, to summarize this slide, very simple takeaway. Your client submits a job. It copies the binaries, mappers, and the reducer implementation along with the configuration file and the input and output part. Okay? It copies the binaries to the HDFS. It copies the binary. When I talk about the binary, it is nothing but a map job that we are told. Okay? And as I mentioned, a job tracker, he creates an execution plan. Which task tracker will execute the mapper and which task tracker will execute the reducer. And it also keeps updating the status. What does the task tracker does? He actually does the job. He does the map and the reduce job, and he updates his progress back to the job tracker. Okay, now I hope you remember this. Okay. So why have I got this into, why have I all of a sudden introduced an HDFS slide between a MapReduce? All I wanted to explain was the racks. Okay. When we talk about locality, remember this slide or just have a recap. If you can see, you have data 01 block, okay, which is split into 1, 2, 3, 4. So within one rack, one file was split into different blocks. Okay, and the blocks, if you can see this, let me get this. If you can see this data 01, this data 01 has got block 1, 2, 3, 4. Okay, 1 is here, 2 is here, 3 is here, 4 is here. So whenever we run a MapReduce job, the job tracker makes sure the data is available within one rack. Okay, it makes sure it is designed in within itself that if it is available within one rack, okay, if it is available within the same compute and if it's available within the same rack, it will make sure first it will spin up the task trackers on the data where it is all the entire blocks are available in one rack, so that whenever you have a shuffling and the sorting phase, the bandwidth between the computers are less. Or else, if you let us say I'm computing a MapReduce job or I'm computing my word count on this data 01.txt file, okay, and with the blocks are available within this same rack, I can easily compute within this. I can start the task trackers within these 4 machines and I can get the job done. Let us say if one of the machines has failed, and let us consider this guy. This guy has failed, okay, and I don't have, it also has failed. Now I have 1 and 2. I need to look for 3 and 4. The 3 and 4 are available on the next rack. So the job tracker, it triggers the task tracker on this machine, okay, and this machine, and this machine. Or else it is capable now that, okay, now that if you can see 1, 2, 3, 4 are all available on rack 2. So it can trigger the task trackers on this and this rack. Okay, either way. If it doesn't find the blocks within rack 1, it found some partial blocks. Let us say it found just 1 here and did not find some other blocks, it will go and pick up the blocks from a different rack. So all these are built within your MapReduce as such. Okay. So you should understand like the data locality, and if the data is not available within the local compute nodes or the rack, it can also trigger, it can pick up the data from the next rack and different nodes as such. Okay, that is what I wanted to highlight from this slide here. Now, we have been building as such. Okay? Initially, I just gave you an analogy. Next, we broke up that into word count, and then I introduced you to MapReduce phases, and then the MapReduce phases, when they get executed and who execute the MapReduce phase, are nothing but the job trackers and the task trackers. Now, I will further elaborate to explain how the entire who executes what as such. Here, few things like the record reader, map method. These are methods, and some of them are just phases. So this slide I'm just trying to ease and then explain further what are the other phases that are available. Okay. Now, first thing I want to explain here is split. Okay, now you have individual files. Okay, Hadoop, what Hadoop does is, Hadoop divides the input to a MapReduce job into input splits. Okay, now one map task is created for each split. One map task for each split. So what does this map task does? The user-defined map function is executed for each record in the split. First thing is, your Hadoop divides your map, or it divides the input. Okay, it divides the input to a MapReduce job into splits. First thing. So if you have 4 lines, okay, if you have 4 lines, the 4 lines will be, if you have a paragraph, one paragraph has got 4 lines, the entire paragraph will be split into 4 lines. Fine. And these individual lines will become an input to your MapReduce job. And this one map task, okay, is created for that one line. For individual lines, your user-defined function is executed. Okay. Now that is, you don't have to do anything about the split. Split phase uses an input format. Okay. To bring out HDFS and the split. Okay. Now, what I mean to say is, you don't have to do anything. Is your input format has a method. Okay. Your input format has got a method which splits your data into individual records. So it is not that you have to do any action as such. What I'm trying to explain here is, your map method picks up individual split, or it expects individual splits as such. Now, who will feed that individual split? It depends on the input formatter. As I mentioned, by default, we have a text input formatter. This guy takes care of splitting a paragraph into individual lines and feeding that individual lines which your map is expecting. Okay. So default input format is text input format, which breaks up text line by line. Okay. So now each record is a line of input. As I mentioned, there are different input formatters, binary input formatter, and database, I think database formatter, and I think there is also record input formatter. Okay, there are quite many input formatters that are available. Now, the client application running the job calculates the splits for the job by calling getSplits. You have a method called getSplits, okay, which calculates the splits, okay, and then this sends them to the job tracker as such. So what all things the job tracker gets is the input split, okay, and also the storage location, because whenever you're passing, when you're running on the client, you also pass the input location. So you got the job tracker gets the split from the input location, and also how many bytes it has to. Usually the split size is same as the HDFS block size. Usually the block size is 64 MB. So by default, your split size also will be around 64 MB. Okay, it matches. It's easier that way, so that the block size and the split size match, so that you can pick up one split as such. Okay. Now that we have splits with the storage location, the job tracker has the splits as well as the storage location. The job tracker uses this information to schedule map tasks that will process on the task trackers. Okay. Now, what happens is, whatever individual lines becomes an input for the map as such, map method as such, which will be running on the task tracker. Okay. Now, apart from this, there is something called record reader. Okay, this is pretty much interesting as such. So what this guy does is, so there is a method called create record reader. Okay, now the task tracker map passes the splits. We have input splits from the first stage, right, to the record reader. Okay, and to obtain there is a method called create record reader, which returns record reader. Okay, and all this record reader does is, it is like a loop through. Okay, the map task uses this record reader to generate a record of key value pair. Okay, now this could be a little bit cryptic here. So what I will do is, I will go back to the example that I mentioned here. Now, it's easier to explain with this guy here. We have a paragraph. Okay. Individual line is a split, which your map is expecting. Now, what does your create record reader does? Okay, the create record reader creates a record reader. If you go to the create record reader method, it generates a key value pair that is passed to the mappers. All it does is, it's picks up the splits are given a key value pair and it's passed on to the mapper. The mapper can go to mapper does a loop. All this mapper does using this record reader, all this map method using their record reader loops through individual words. That is all it does. It's as simple as that. The record reader is a loop which it create. The map uses this record reader to loop through individual words. It's as simple as that. But when you try to go through the definition either on Hadoop or on Hadoop definition book, it's quite much complicated to understand. But all it does is, the map method uses the record reader to loop through individual words in the split that we have passed as an input. Okay. Now there is another phase called combiner phase. Okay. Now, why do we need combiner phase? If you go through the previous slide that I explained, between the map and the reducer phase, there is a shuffle and a sort phase, which makes use of majority of the bandwidth. So you can also have a combiner method, which will sort of reduce the bandwidth. Okay, that is why you have a combiner method. This is not, you have to implement this. Okay, you have to implement this combiner method, and you can reduce the bandwidth for the sort and the shuffle phase. So otherwise, there is nothing much about this combiner phase. And yeah, you also have something called partition functions. I've already introduced this. If you can see, whenever I was showing mappers and reducers, the data was partitioned. Like in the first phase, the data was partitioned from A to N and M to Z or something like that. So the data is always partitioned, and the partition functions, whenever there are multiple reducers, okay, whenever you have multiple reducers, the map task will partition the output. Okay, each creating one partition for each reducer task. So if you have 3 reducers, you will have 3 different partitions. It's as simple as that. If you have one reducer, there will be no partition. All the data will go to all the output from the mappers will get into the reducer phase. Okay, if there are 2 reducers, there is a partitioner who pitches in, and he will go ahead and partition your output from your mappers, and he will send the data to 2 different reducer job. Okay. Now, we have already come across what is sort and the shuffle phase. Okay. So there is nothing much now that in this case, in the sort and the shuffle phase, right? All it does is, it is primarily the sorting of the data, which is called a shuffle phase. When we talk about sorting, because there are numerous mappers. Okay, there are numerous mappers, and the data gets shuffled from one mapper to the other, and the job tracker keeps a track of how the data is actually being sorted. So the entire sorting phase, the entire sorting that happens on the data is called a shuffle phase. Primarily, it is not shuffle and sort, it is just a shuffle phase that happens between your map and the reduce. Okay, and we all know what is reduce. The reducer is just an aggregation. It creates an aggregation of whatever that we have fed in. Okay, and finally the output is written back to the HDFS. And how will the task tracker know where the data needs to be written? Because whenever the client, whenever you're invoking the MapReduce job, you pass the input as well as the output folder. So the task tracker will pick up this and write the output to those specific locations. Okay, so this is how the entire data works. If you have an input formatter, the entire paragraph is split into splits, and this individual line will go to the mappers, and the mappers uses the record reader to loop through individual words in one string. Okay, and add key and a value to it. And the partitioner, if there are multiple mappers, the partitioner, what it does is, it, depending on the reducers, it partitions the output of the mappers to individual reducers. And what happens in a shuffle phase, it is just a sorting of the data that happens. Okay, and the reducer aggregates the data, and finally you have an output. Okay, so this is how the entire data flow happens within your map and reducer. So a few things that I have introduced apart from MapReduce is nothing but record reader. I want you to understand there is something called record reader which goes through your split. Okay, and also understand there is something called split. Okay, so splits, record reader, and partitioner. These are some of the takeaways from this slide here. Okay, because you have already been introduced to job tracker and task tracker and what it does in the previous slides. So finally, all put together, you know how when we copy the file to the Hadoop distributed architecture, you use name node and populate the data into different data nodes. Now, when you're executing MapReduce, we use the job tracker. The job tracker queries the name node, picks up, it gets to know where the data is located, passes the information to the task tracker, and the task tracker goes to the task tracker execute the job on the data that is residing on the data node, and then you get the output. So that is how you have your name node. If you understand, the name node and the data node primarily comes into picture when you are copying the data to HDFS. Apart from this, they also are made use when you're running your job tracker as well as your task tracker. Okay. Yes, so I guess I have covered everything here. I'm just checking out if I have missed out any points. So yes, so this is all I had for today. So I think we are open for questions now. Yep.
Sunil, I guess there is a couple of questions in the message window. What is the rack and things like that?
Okay. So in a usual architecture, right? So you can have multiple. It is just a segregation of your computers. Okay, I'm just trying to explain this in a very trivial way. It is just a segregation of your computers, wherein within one rack you can have a network switch, and all these collection of compute nodes under one rack. Okay, uses this network switch, and they form their own network. So to make it much more simpler, our rack houses more than one computers underneath. It can also have a network hub where all these n number of computers housed under one rack can interact among themselves. Okay, they form their own cluster as such. Okay, so it's a collection of your compute nodes or computers that form a rack. Yes, I'm going back to the chat. Okay, the clusters have already been explained in our previous session. Okay, so I would be glad if you can just go back to that session and understand, because I've explained both cluster architecture as well as the legacy architecture that usually we use. Okay, both have been very well explained there.
I see.
Yeah, hi.
Can we customize this partition as you said?
Can we?
Partitioner. Partitioner, right?
Yeah, you have something called partitioner, yes?
We can customize that partitioner to limit these words. The words are coming over 5 times goes to this over.
You can write your own. So what you are trying to do is, can you customize? You can write your own user-defined partitioning function.
Yes.
You can control the entire thing using a user-defined partitioning function. But you know what happens is that default partitioner. Sorry. Yep.
Can we get any example of this partition?
Or maybe we will keep this as such. Okay. Maybe in one of the sessions we can cover that as well. Okay, but normally the default partitioner, I just wanted to highlight this very quickly. Now that you have bought the partitioner, you have a default partitioner that usually it uses, which uses the keys using a hash function. So I believe because whenever we are playing with numbers, right, the default partitioner actually works very well. So unless until you have a specific need, I'm not sure when you will go ahead and write your own user function. But certainly you can.
Then we need to do this partition.
Yeah, then certainly you can. Certainly you can write your own user-defined partition function. Yes, you can do that.
Do you have any examples of this partition? I mean, like coding.
You're saying, do I have any example for user-defined partitioning function? Am I right?
Yeah.
No, at this point of time, I do not have anything. But as I mentioned earlier, we can cover that in one of the sessions. Okay? So, any other questions?
Okay, so guys asking for the previous sessions and the links, the PowerPoint. So follow the group. I'll share the. So for the we upload all the PPTs in the group section itself, the file section, and we post the recordings in our YouTube channel. So if you just take some time to go through the posts in the group, you can grab the details, the files for this session and as well as all the previous sessions. And one more thing again for a few people here is this is targeted basically for the beginners, okay, who are getting started. So I understand that most of you might be working in real life projects using Hadoop. So specific questions regarding niche technologies, like somebody asked about Cassandra and all. So I guess this is not the correct place where you can, or this is not the correct time either where we can get started with addressing real life problems. So this is focused more towards getting people started. So if you guys like, you can just skip off the basic presentations that we are doing to start with. So as soon as and when we the group matures and we take the people along with us so that they can attain a some level of expertise in the technology, then maybe we can, based on need, we can address specific scenario based or niche technology based questions and presentations. So I guess we are good here, Sunil. So I'll post the recordings in maybe 15-20 minutes, and if you have followed the last slide, the next session that we will have is that will be about a lab, and that will be about setting up Hadoop on a multi-node Linux cluster. So I don't have the date specifically as of now, so as I fix on the date, I'll share the dates as well. So it will be so now that we have covered the basics, the theory part of the core Apache Hadoop, the HDFS and the MapReduce, maybe it's a good time for us to get started with a little bit of practical. So the next session will be focused on setting up a multi-node Hadoop cluster. So yeah, that's all. Thanks for joining today, and hope to see you soon again. Bye-bye, guys.